Now the next question related to the Euclid division algorithm is to show that any positive odd integer is of the form 6q plus 1, 6q plus 3, 6q plus 5, where q is some integer. Now how do we solve this kind of a problem? We know from Euclid's division lemma that for any two numbers a and b, a is equal to bq plus r, where r lies between 0 and b, 0 included, where q and r are also integers, a and b are also positive integers. So any two numbers a and b can be written in this form. Now since any two numbers a and b can be written in this form, we can let a to be any positive integer, right? And b can be 6. B can be any number. Since this is true for any value, any two values of a and b, if we take b as 6, it is still going to be applicable. It is still going to be true. Why did we take 6? Because in the question we have to prove that any odd positive integer is of the form 6q plus 1, 6q plus 3, 6q plus 5. So we took b as 6. In that case, what will any positive integer be written as? It can be written as 6q plus r, where r would lie between 0 and 6 because b's value has become 6. So what are the possible values of r that you can have? There could be a case 1 where a is equal to 6q plus 0. R can be 0, so it will be 6q. The second case could be that a is equal to 6q plus 1 because r can take all values, all positive integral values from 0 to 5. It cannot take 6 because there is no equality sign on number 6. So we get the following cases. You have these 6 cases. For any positive integer a and b is equal to 6, you can have these 6 cases. There will not be any more case because it will start violating this particular lemma, which is always true. Euclid's division lemma is always true. So this has to hold always. And in that case, there could be 6 possibilities that are there for these two choices of numbers a and b. Now what is 6q? 6q is 2 into 3q, right? Q and r are also integers. So q is an integer. So this is an integer. 2 into any integer is an even number, right? 6q plus 1, you cannot have it in the form 2 into. Here if you take 2 common, you get 3q plus 1. This again is an integer. So 2 into any integer would again be an even number. Similarly for this, you take 2 common, so you have 3q plus 2. An integer, 2 into some integer will always be an even number. So for the remaining 3 cases, if the number is not even, if an integer, positive integer is not even, it has to be odd. If a positive integer is not even, it has to be odd. So for all the 6 possibilities that you had, 3 cases were even and the rest of the 3 cases were odd. So what do we figure out? We figure out that for any positive integer, it can be written in for any odd positive integer. So for these 3 cases, a will always be odd. So any odd positive integer can be written in the form 6q plus 1, 6q plus 3, 6q plus 5. Other even forms would be 2 into some integer. So this is how you prove it. You can use the Euclid's division lemma to prove that any positive odd integer is of the form 6q plus 1, 6q plus 3 and 6q plus 5. Let's take another problem. Now this next question is about proving that the cube of any positive integer is of the form 9q plus 1 or 9q plus 8. And how do we use Euclid's division algorithm? Again, Euclid's division algorithm or lemma would be this. we have to use it. So let a be any positive integer as we took it in the last question. For the value of b, you would say that we should take it as 9 because we have to show it in the form 9q and 9q plus 1. But there's a short way that you can do this question. Since we have to find out the cube of that number, so if we take b as 3, if we take the value of b as 3 and then we do the cube of number a, over here the factor of 3 would become 3 cube, that's 27, which includes 9. Hence, we can get 9 even if we take b as 3. Why we take b as 3 and not as 9? Because if you take b as 9, then you will have 9 cases, 9 different forms of the number, and for each form you will have to find out the cube and figure out what the form is. That will make the question very lengthy, solution very lengthy. Hence we take b is equal to 3. And in this case, the total number of cases will just be 3. So that's the utility of this method. The case 1 would be a is equal to 3q plus 0. So that's 3q. And in this case, we will have to find out the value of a cube. That's the cube of the number, which will be 3q cube. It's 27q cube, 9 into 3q cube. Now this is an integer, 3q cube is an integer, hence this is of the form 9k, where k belongs to an integer. This epsilon symbolizes belongs to and z is the form for integer. So it reads k belongs to integer. So k is any integer. So if the number is of the form 3q, you get its cube as 9k. Here you can understand why we took b as 3. Because when we have 3 and we do the cube, 9, the factor of 9 comes by itself. Hence, we do not need to create 9 cases to find it out. Now, the case 2 would be a is equal to 3q plus 1. So, you have a cube is equal to 3q plus 1 whole cube. That's a plus b whole cube. So, you get 27q cube plus 1 plus 3ab, so it's going to be 9q and a plus b. So if you take the factors of 9 together, you get 9 common. Here you have 3q cube, from here you get 3q and another q plus the 1 over here. So this again is an integer, and what is the form of this number? It's 9k plus 1, where k belongs to some integer. So if the number is of the form 3q plus 1, the form of the cube that we get is 9k plus 1. So if this is equation 1, this is equation 2, you take case 3, where a is equal to 3q plus 2. So you have a cube is equal to 3q plus 2 whole cube. So you have a cube plus b cube plus 3ab. So it will be 9 into 2. It's 18q, 3q plus 2. And what do you get? You get, if you keep the 9 factor together, here you have 3q cube plus here you have 6q square, right? And you have 4q, right? So you have 4q and you have the 8 separately. So you have this being an integer, this becomes of the form 9k plus 8, where k belongs to some integer, and this is equation 3. And what do we get from the equations 1, 2 and 3? That for any positive integer, its cube will be of the form 9k or 9k plus 1 or 9k plus 8, where k is some integer. In the question you have q, I just have changed it to k. So you can change it, you can keep it as q or you can make it as k over there. So this is what we had to prove. Now the next question is to show that any one of the numbers n plus 2, n or n plus 4 is divisible by 3. Now again we will be using Euclid's division lemma for this, And here again you have any number, since we have to use divisibility by 3, so we take b as 3. So what will be the case 1? For any positive number can be of the form 3q, right? Case 2 would be 3q plus 1, and case 3 would be 3q plus 2. A is equal. Right, these are the 3 cases that you can have. If the number is of the form 3q, since it's given n, so let's take it as n and not a to create lesser confusion. So any number n can be of the form this, right? Instead of a I have written n, and instead of b I have written 3, because that is what you have to use. Now when the number n is of the form 3q, what are the 3 numbers that we have to check? We have to check n plus 2, n and n plus 4. So if n is 3q, what will n plus 2 be? It will be 3q plus 2. What is n? It's 3q. And what is n plus 4? It's 3q plus 4, which is equal to 3q plus 3 you put aside and 1, which makes it 3q plus 1 plus 1. Why I did it? I'll just explain. Now if the number is of the form 3q, these are the 3 possibilities for the number n, right? So when n is equal to 3q, n plus 2, n and n plus 4, we have to find out that only one of these 3 numbers is going to be divisible by 3, not the other 2. So we take n plus 2, in this case it will be 3q plus 2. Is it divisible by 3? No, because when you divide it by 3, the remainder will be 2. Hence, this is not divisible by 3. Is this divisible by 3? Of course, when you divide it by 3, the remainder is 0 here. So this is divisible by 3. Is n plus 4 divisible by 3? When we simplify it here, we see when we divide by 3, we again will be getting a remainder 1. That's why I simplified it in this form. So the remainder is going to be 1. Some of you might say that the remainder straight away can be 4. No, the remainder will always have to be less than 3, right? So this is not the standard Euclid division lemma form. We have to reduce it to the standard form and then figure out what the remainder is going to be. So here the remainder is 1. So this number is not divisible by 3. So when the number n is equal to 3q, then only n is divisible by 3. Other 2 are not divisible by 3, which is what you have to prove. In the second case, n plus 2 will be 3q plus 1 plus 2. What does it become? 3q plus 3, which is taking 3 common, you have 3q plus 1. N becomes 3q plus 1, and n plus 4 will be 3q plus 1 plus 4, which is 3q plus 5, which is 3q plus 3 plus 2. You have 3 common, q plus 1 plus 2. So here, for this number, this is divisible by 3 because when you divide it by 3, the remainder is 0. Here the remainder is 1, so it's not divisible by 3. N plus 4, again if you divide by 3, the remainder is going to be 2. It's not divisible by 3. So in this case also you see that only one of these 3 numbers is divisible by 3, the other 2 are not. Similarly, for the case 3, you have n plus 2 will become 3q plus 4, which is 3q plus 1 plus 1. N will be 3q plus 2, and n plus 4 will be 3q plus 2 plus 4, that is 3q plus 6 is equal to 3q plus 2, which is divisible by 3. So this becomes divisible by 3, whereas this number and n plus 2, this number, these 2 numbers are not divisible by 3. So we see that in all the cases, only one of the 3 given numbers is going to be divisible by 3, which is what we had to prove.